I invite my dear friend Eva Deelman to give the first presentation of Multicore World 2026. And as I said before, don't be shy, don't be humble. The whole idea is to participate and share. All right.
Thank you so much for the introduction, Nicholas. And for the invitation to be here. And the presents, the presents, I got chocolates and cheese. Both got to start with a C and go together, so thank you. And it's always a pleasure to be here at Multicore World and to participate in the discussions and listen to the various presentations. So today I'll be talking about reimagining workflow management. And so kind of to set the stage, I'll talk a bit about how we got to the reimagining phase by looking at where we've been with Pegasus and the new effort that, which is a workflow management system I've been working on since 2000. Also, I'll talk about Pegasus AI, which is a new system that's been funded by the National Science Foundation to infuse traditional workflow management systems with AI. And then the reimagining really comes into the agentic workflows, which we started a few years ago when agentic was not a thing, and we're really getting inspiration from swarm intelligence and looking at how we can use swarm intelligence in workflow management systems. And then looking a little bit more into the future of how we can also impact self-driving labs, and I'll talk a little bit about that. So as I mentioned, we started working on Pegasus, the scientific workflow management system, some time ago. And it's a system that allows you to run complex scientific applications on heterogeneous environments. So you can run on your laptop, you can run on an HPC system, a cloud. And the features that it has, it does a lot of the data management on behalf of the user. So it infers where the data how the data needs to be transferred from where. It adds these data to the workflow management and to the workflow itself, and then it enacts it. We track provenance of what's happening with the system. This is something that's very important when users and scientists want to interpret the results. So we have tracking everything that's happening. And obviously, error recovery is also an important part of what we're doing. If you're looking at the basic concept of Pegasus, we have the notion of an abstract workflow, which is a specification that doesn't have resource information in it. So it really captures the scientific recipe of what a user wants to do. So it could be talking about running a particular simulation on a particular set of data, but without actually saying where they want to run these computations. When Pegasus takes this high-level description, which is in the logical space, and you can think of it as compiling it down to something that's executable across the distributed environment. And it could be compiled down to run on one machine or multiple machines. So then you see on the left in the graph, you see where the Pegasus adds node to create directories on the remote end, to add nodes to do the data transfer, and then it transforms the computational nodes into something you can submit to the system. Then it stages data out and registers it. If on the right-hand side of this graph, you can see that you executing things maybe on a different location, so then you have additional nodes to do the data movement. And all this is done seamlessly for the user. So then with this type of concept, you can do a variety of things. You can just do a straightforward compilation. You can also optimize the workflow for performance. And so you can do a variety of different optimizations for data placement and also clustering tests together and others. So with this type of setup, you can run very simple workflows, which take some historical data about the air quality at a particular location. You can prepare various features of the data. You can train a model and then use it to forecast what in the next 24 hours, what kind of air quality you can get in some location. You can then visualize it. So this is a very simple workflow. It can give you a nice graphics for a particular location I think it was in Germany, and you can see that the air quality was not very good. So you can do simple workflows like that. You can run workflows taking data from sensors in real time and also doing this type of modeling. You can also run something much more complicated. This is an example of a workflow that's been run by scientists of a statewide California Earthquake Center, where they generate seismic hazard maps of California. This is a map of Northern California that they generated a couple years ago. They ran, to generate these maps, they ran large-scale simulations followed by post-processing. They ran for 45 days to generate these two maps of Northern California. This is one of them. They ran on the GPUs on Frontier, which is an exascale system at Oak Ridge National Labs, and they ran for 55,000 node hours. And thanks to Dan, they also ran on Frontera on the CPUs with 125,000 hours. One thing to note is they didn't get any priority bumps, so didn't ask for them. This is all done through the automation that's provided by a workflow management system. There was about 1 petabyte of data that flowed through these workflows with 9 million files staged back to USC, where the scientists were working on them. So this gives you the scale of what we can do with a production system. However, we're thinking that with AI technologies, we can really improve both the user experience, but also the performance of scientific workflow management systems. And so we've been funded last year by the National Science Foundation to look at what are the opportunities to add AI into the entire workflow lifecycle, from workflow composition through estimating what kind of resources are needed to execute the workflows, looking at issues of anomaly detection. We're using AI techniques. Then looking at once you detect anomalies, how does the system adapt? And how do you learn also about workloads over time? So you have a process where the models can learn about how the users are structuring the workflows, or maybe a whole collaboration. So then you can use that information also to build systems that are more amenable to AI technologies. For this work, we assembled a team from scientists at University of Tennessee, Knoxville, UMass Amherst, and University of North Carolina, Chapel Hill, to look at the various aspects of a problem. So one of the things that we've been, and we're looking and developing these technologies that can be put into the production system, but we're also changing the way we're thinking about workflow creation. So this is our latest thought on the system. This came off the presses last week, where basically you have this initial workflow idea that you can sketch on a whiteboard piece of paper, and then you take the executables that you know you need to put into that, the input data, and you use AI. So, for example, Cloud Code has been very good for that, but other LLMs can be used as well to generate what we call a workflow generator, so something that will actually write out the workflow. So Pegasus provides a number of different APIs that can be used to do that. We have a Python API, which fits in very well with the LLM models. So we recommend using that. So you generate the workflow, generator which generates the workflow. Then we can have various checks to check for consistency, see if everything works well from a textual point of view. The user then next needs to test the semantics. So you test maybe on a small case, seeing whether the workflow gives you the results that you want. And then you can scale up the workflow. So with this, you can actually accelerate the workflow generation quite a bit. We had somebody that was a novice to Pegasus generate, I think, 4 or 5 different workflows in 3 days, from beginning to end, collecting results, collecting data to the input data to the results. And obviously, the crux of the problem is the validation process, right? So now it's easier to generate the workflows, but you need to be able to validate that they're actually giving you the results that you want. For the production system, we're also adding things on towards the end phase of our execution. So we're putting LLMs to help users debug errors. And in this case, we still give the statistics that normally Pegasus provides to the users and helpful hints of what's going on. But then the LLMs can provide us with better information, something that's more amenable to novice users. And good thing about being around for quite a while is that and being an open source project, all our documentation, everything is available and has been available since 2001. So you can use an out-of-the-box LLM to do the workflow generation and to do this analysis. Also, if you want the workflows when you generate them to be more grounded, you can provide them with previous workflows that are vetted, that have particular structures that you think will be amenable to your work and that will improve the quality of the workflow generation. So as I mentioned, my talk is about reimagining workflow management systems. So we've been, although we are improving the production systems today, we're also thinking about how the systems will look like in the future. And what we see on the ground is that we have a lot of different types of workflows that are coming up that are taking more data from distributed sensors and distributed resources. You have also more locations and more opportunities to do the computations, to do the data transfers. So the entire ecosystem of these heterogeneous resources is scaling incredibly. Thus, we need to rethink of how we're doing workflow management. And to do this, we assembled a team that has expertise in AI and also resilience. So that's an issue that comes up when you're trying to distribute things at a large scale. Also from networks and simulations and others to look at this issue. And we came up with an idea that's been funded by DOE in 2023 to reimagine the system where we have, you don't have a centralized entity orchestrating the work, but you have a distributed system where the work is described in what we call a pool of a workload pool. It's still distributed, but it's a common view for various agents to look at to pick off the jobs that they can do. And then also agents can put things into the workload pool. So for example, you can have a network agent that looks at that there is a data transfer that needs to be done between two systems, so it can pick up that job, do the data transfer, and provide the results. The next agent, for example, at the edge can decide to pick up the jobs that are amenable to the system that they operate. And then you can also have instruments being part of this ecosystem of workers, of agents. And they, as you run an experiment at a microscope or some other resource, the data can be, and jobs can be automatically put into this workload pool to be executed. So we're thinking of this system, and we started with the idea of implementing it and exploring it for swarm intelligence. We liked it because it has this nature-inspired elegance and coordination across various agents. It has properties that we like in a distributed system that's resilient, so self-monitoring and self-healing. It has the decentralized coordination, but it has also a variety of challenges. So it often comes slowly to consensus. The agents often have limited perception. They have network challenges, so network goes down, then the cooperation can be also suboptimal. So given all the benefits and drawback, we started thinking of different ways of improving on the swarm intelligence. And in particular, we looked at infusing these swarm intelligence agents with traditional distributed systems algorithms for scheduling and resource management. We also thought we can take advantage of what's happening in the AI world and add additional capabilities to these agents as well. So this is what is agentic AI. And looking at how we can infuse the distributed techniques with what's happened, which was developed for the swarm intelligence agents. And in this system, if you saw the previous picture showed you and actually it can be seen in this one as well, you have agents that can have various capabilities. Some are running at the edge, which would be very lightweight. But if you have agents that are running an HPC system, they can run large language models to do the inference with more reasoning capabilities. So in our problem formulation, we have this original formulation where we have distributed by the kind of global view of the system, so that where the agents can observe each other. We rely on a resilient database to provide this global view, and the jobs as submitted to this one entity. We're also looking at a solution where there is no shared state. And this particular solution was motivated by what's happening across Department of Energy systems, where you have various sites with exascale and leadership class facilities, and users submit jobs to the local system. And from there, we can see agents looking at what's happening in their own system, but also a system with others, and they can coordinate the distribution of a workload across the various agents and systems. So these are two views that obviously have some benefits and drawbacks. So the shared state, it's easier to assess what's going on overall and rescue jobs that maybe are not progressing. You can, however, there are some issues of there's an increased delay between the jobs being submitted and being picked off by agents. In a local state, you can do it pretty fast because a local agent can just submit to their own resource. But you don't have this kind of view of what's going on. So if the agent at the resource goes down, then there's a challenge of managing the workload. So there are so the resilience is more of a problem. So there are different aspects of this problem, but however, there are still things that are in common. So you have the issues of monitoring perception to figure out what's going on. Reasoning of that the agents need to do, the communication, so how the agents communicate with each other and come to a consensus, and then what actions they need to take and issues of learning. So we formulate this problem as in different ways, but with a mathematical foundation, and then we decompose the various challenges into the challenge of job selection from the pool, job scheduling onto the resource. So if you're an HPC agent, even if you pick up a job, you need to schedule onto the resources that are available to you. Looking at issues of consensus algorithms, so how do the agents agree amongst each other what to do, and also overlay networks. So you don't want all the agents talking to everybody else. You want to form a network that actually provides efficient and resilient communications. In order to be able to evaluate the approach, we're using simulation, also emulation on a fabric testbed, which is a testbed in the US, programmable testbed in the US you can use for large-scale experimentation on distributed systems, and also system prototyping. So I'll just quickly go over some of the things that we are currently working on and some of the results that we had. We looked at consensus algorithms. We developed a greedy consensus algorithm, which basically builds on some of the existing solutions, such as the practical Byzantine fault-tolerance algorithm, but also, so it has the similar phases as that, but it has different ways of proposing selection of a job, so that in this case, all the agents communicate with each other. They look at the costs of what would be to schedule a job by the other agents, and then they come to a consensus and commit based on the consensus of what they found during the communications. With this particular greedy approach, we improve the scheduling latency quite a bit by over 63%, and also the time. So the time from the job being scheduled to the pool to the job being executed. And also we improved the idle time by 64% almost as well. So idle time, it's the idle time at the resources. In this case, we made a number of assumptions. So each agent knows the capabilities and the workflow load of the other agents, so prior communications, and can compute these functions for job selection, and all the agents communicate with each other. So we are now relaxing this assumption where the agents can learn about other capabilities over time. And also we're providing more selective communications through network overlays. So in this case, we're building ring topology. We build rings in a distributed fashion. This is just an example of a sequential ring construction within a particular subdomain of a network, where the agents are using Q-learning to basically decide which node to connect next, and they get rewards if the diameter of a network is reduced, thus making short communications. This is also based on the latency that's being measured across the network. We did experiments with a fabric testbed. As I mentioned, this is a distributed testbed in the US, which also has nodes in Europe. And we found this construction, Q-learning-based construction, is better than some typical algorithm. So now we also have an issue of scheduling. So the agent, for example, picked off jobs that are for the HPC system, and it needs to decide how to schedule the jobs. For that, we've been exploring the use of large language models. And this is the prompt that we experiment with various prompts. In the end, we decided this one was giving the best results, where you tell an LLM that it's an expert HPC resource manager, and its task is to schedule. You tell them about balancing the various objectives and how to make decisions. We compared that. I don't have too much time to talk about everything, but we compared it to other algorithms, such as the simple first come, first serve, shortest job first, and the Google OR tools. And it does well in some cases, not as well as others. However, what's really nice about these LLM-based schedulers is that they allow you to basically recode the policies using natural language. So really quickly you can decide, shift from one type of operational mode to another. So I mentioned progression of automation. So I talked about Pegasus AI agentic workflows. And now I want to talk a little bit in the time remaining about self-driving labs and how we can think of putting these agentic workflows and concept from agentic workflows into self-driving labs, where you have a particular, could be a microscope or some other more complex type of instrument, where you're running a number of experiments and you're using AI to drive the decision of which experiment to do next. And Ben, if you want to know more about self-driving labs, Ben Mintz here in the audience from Oak Ridge has been doing this for a long time. So we're thinking about, in this work with agentic workflows, how we can apply some of the concepts to this type of self-driving labs. So you can place the agents, for example, at the instrument, so they can make sure that the instrument is operating well, that you can check the quality of the data that's coming off, and maybe trigger some pre-processing. So this is this agent instrument agent that puts the workload in the pool. You can have an agent that sits at the edge, close to the instrument, that applies algorithms for denoising. It checks for different patterns. It might also start classifying some of the stuff that's seeing under the microscope. And then you also have an agent that's sitting at the HPC cluster, where it can pick off jobs to do this more computationally intensive tasks, such as 3D reconstructions and maybe running simulations alongside these experimental type of data collection to compare the results. Then you can take it a bit further. You can, if you're talking about a system which you have a number of beamlines, for example, in a particle accelerator type of instrumental facility, you can have agents running at the different beamlines, and they can now provide resilience for the primary agent that's doing this initial processing at the edge. So if that agent goes down, you can have others pick up a job without interrupting the progress of an experiment. And you can also take it one step further. You can have these agents learn across the beamline. So if they see some type of new data coming in, new type of data, where they improve the classifications, they can all communicate with each other and come to a consensus, for example, to change out the algorithms that they're using at the edge. So I think there's a lot of interesting things that can be done in this kind of different types of agentic frameworks, and particularly with applying the different types of algorithms for consensus, for job selections and others in a variety of environments. So in terms of future work and what we're looking at, particularly in the area of Swarm, so the Swarm project, we are integrating the various components from the job selection, scheduling, and the consensus and overlay algorithms, and exploring how the system presents itself in term when it has failures, both at the infrastructure level but also at the agent level. We're looking at trade-offs between the kind of the shared state of a global job pool versus the sharing of state across the different agents. We are looking forward to materializing this into a prototype. We can further research and see whether this type of approach to workflow management actually works for real applications. And I'll be very excited also to look at how we can explore these type of systems, distributed systems, in the setting of self-driving labs. And with that, I'm happy to take questions.
Yes. Thank you very much.